Hi, today we continue our discussion on gases. In the last few weeks, we've been looking at ideal gases, where we know that P times V equals nRT. And with ideal gases, we make two assumptions. The first assumption is that there is no attraction between molecules. And the second assumption is the molecules themselves occupy no volume. So the equation PV equals nRT is more properly written P, no interaction, no attraction, times the free volume, the volume between the molecules, is equal to nRT. How does that understanding change our gas equation? So here's our flask, and our flask will have a volume, which is volume measured. Here's the same flask, and here are the molecules inside it. V free is the volume between the molecules, and the molecules themselves have a volume, V molecules. V free equals the measured volume, which is the whole flask itself, minus the volume of the molecules. V free is V measured, and the molecules themselves is the number of molecules times the size of the molecules. So B is the size of the molecules. Okay, that's V free. Now let's turn to pressure. So here's the flask again, and we measure a pressure outside, P measured, and P measured is caused by molecules hitting the outside, but these molecules themselves feel an attraction to molecules nearby, so they're hitting the outside wall less hard. P, no interaction, is therefore greater than P measured. P measured feels the reduction in pressure caused by the outside molecules. So P no interaction is greater than P measured. It is greater than P measured by the reduction in pressure caused by attraction. The attraction between molecules is a pairwise attraction. It's pairs of molecules which lead to the interaction. So P reduction then is first caused by the molecule, the first part of the pair are the molecules about to strike the walls. If we double the number of molecules in the flask, we're going to double the number of molecules about to strike the walls. And if we double the volume of the flask, we have the chance the molecules will strike the walls. So we end up with a first factor, which is caused by molecules about to strike wall. And their proportionality is N over V. But P reduction is caused by pairwise interactions, and now we have to look at the second molecules. Here are the second molecules that are about to that are attracted to the molecules about to strike the wall, And if we double the number of molecules in the flask, we double the number of molecules in the flask, we double the number of molecules that are going to be nearby, preventing, interacting with the first molecule, causing the pressure, measured pressure to go down. So that will be the number, this n doubles, that doubles. And if we double the volume of the flask, we have the number of molecules that are going to be nearby. And so we end up with a second factor. The second factor is from molecules nearby. We can turn the proportionality relation into an equality with a proportionality constant, which is always known as A. P reduction is A times n squared over v squared. And if we now substitute that in for this equation here, we get that P no interaction is equal to P measured plus P reduction, and P reduction is A n squared over v squared. So we have now three equations. P no interaction times V free is nRT. V free is equal to V measured minus NB. And P no interaction is P measured plus AN squared over V squared. Putting that all together, we get P no interaction, which is P measured plus A over n squared over V squared. That's P no interaction times V free. V free is V measured minus NB, and the whole is equal to nRT. And this is the van der Waals equation. And it is the equation for real gases.